Okay, great. Thank you. Thank you so much. Okay.
Okay, well, thank you so much, and I apologize everyone for the delay, and I hope we will go ahead and get started shortly. Instead of the introduction, I'm Ashraf Gorgi, professor at Virginia Commonwealth University, and also a chair of the FES and Technology Task Force. And together, this is our second community webinar from ISIG ACRM. And we're glad to have Dr. Milos Popovic, who will be talking to us today about functional electrical stimulation topic of interest. And we're glad to have Dr. Popovic with us. And Dr. Popovic, please go ahead and get started. Thank you so much.
Thanks, Ashraf, and thanks, Kristen, for inviting me. It's really a great pleasure. And Kristen wanted me to talk about functional electrical stimulation, past, present, and future. And so I tried to put some things together. This is fairly biased perspective on the field. And I'll go through all kind of different things that we've seen in the last 50, 60 years. And hopefully you will enjoy the presentation. What is important for you to know is that I founded a company called MyndTec about 10 plus years ago. So I'm a shareholder in that company. So whenever you see something about MyndTec or MindMove, take that with a grain of salt and having in mind that I'm deeply involved with this institution. So I'll start with some basics, and I won't dwell too much on that, but I think it's important just very briefly to go what electrical stimulation is all about. So this is a surface electrical stimulation type of a situation where you have a skin, you have stimulation electrodes on top of the skin, and you have nerve bundle, which consists of multiple nerve fibers that you want to activate with the electrical stimulation. And the reason why you can do that is because the nerve fiber itself has a negative charge, which is inside, and has a positive charge, which is on outside of the nerve. And the normal voltage of that difference is about minus 90 millivolts inside the nerve with respect to the outside. And if you can disrupt that, you can actually generate action potentials. And that's what the electrical field does. It actually provides negative charge to the outside of the nerve. That positive charge outside the nerve decreases in volume or magnitude. And then as a result of that, that causes an action potential. Sodium, potassium pumps open, and you have an action potential which goes right to the muscle and causes a muscle contraction. That's the fundamental physics of it. Now, this is my drawing of biceps muscle. Sorry if it is not the most eloquent way of doing it, but you can activate the muscle essentially by putting electrodes on top of it and providing different types of electrical pulses to it. As long as you provide negative charge to the nerve and the nerve bundle, you can actually generate action potentials. These particular pulses are not those which we will recommend you to use. And the reason why not, these are not charge balance, which means you're providing charge to the tissue and then you're pulling the charge out, or you're not pulling at all as the pulses at the top. And over time, if the charge is accumulated in the tissue, it can cause tissue breakdown and all kind of chemical processes that you would like to avoid. The sinusoidal pulses are not particularly bad. The only thing is, because the rest time is very slow, they're not the most effective way in generating muscle contractions. The ones that we have historically found quite effective are those which are symmetric pulses or asymmetric, but both of them are charge balanced. And when you apply the symmetric ones, this is an important thing. It really matters if you apply the one or the other type, symmetric or asymmetric. So if you apply symmetric, you're essentially generating contractions under both of the electrodes, because both of the electrodes have this negative phase, which is quite substantial. However, if you use asymmetric pulses, you're only generating the charge under the negative electrode. For those of you who are using stimulators, these are the electrodes which are usually labeled red. And those of you who use MindMove stimulator, this is the electrode which is labeled black. Okay. And all of this stimulation, it doesn't matter which one, you actually generate some degree of discomfort. And the reason why they generate discomfort is because these pulses equally activate all types of peripheral nerve fibers, all of them. And as a result of that, all the fibers which are responsible for transmitting from periphery to the central nervous system information about pain or discomfort, they also get activated. And many of the patients who actually receive these pulses essentially feel some degree of discomfort. We thought for a very long time that this is given. There's not much we can do about it. The pulses are given. These are the safest pulses as FDA recommends. But recently we had an interesting surprise, like all the good things that happen by chance and by being in the right spot in the right time and doing something ridiculous. We discovered there are types of pulses which are not so painful. The key to these pulses, they have extremely fast rise time, which is in nanoseconds. In the steady state, amplitude is very low, but 10 times lower than in the normal pulses. As a result of that, what happens is that when you stimulate peripheral nerve fibers, because these pulses are executed very fast, they actually activate all the faster fibers, but they don't activate the slower fibers, meaning that the pain and discomfort that you will normally feel is much less intense in this type of pulses. So there's a paper which we just recently published on the topic, and you can see what is the perception of the patients. But clearly, you can have pulses which cause much less discomfort than the conventional ones. What is electrical stimulation good for? There are tons of things that people have been using it for, and these are some of the things that are actually commercially viable and practical. So these are cochlear implants, deep brain stimulators, vagus nerve stimulation, hypoglossal nerve stimulation, spinal cord stimulation, and various FES systems like for cycling, grasping, and walking. I'll spend more time on that in the rest of the presentation. Just very briefly, the cochlear implant is used to directly stimulate auditory nerve in people who are profoundly deaf. This system is probably implanted in tens of thousands, hundreds of thousands of patients worldwide, extremely successful. Deep brain stimulation is also implanted in a large number of patients. It's used to treat essential tremor, Parkinson's disease, even obsessive compulsive disorder, and other things. Vagus nerve stimulation is something fairly new to the market, and fairly new, maybe like 5-10 years, and it's used by stimulating vagus nerve, reduces the number of seizures in patients who have quite repetitive and high number of seizures. They may not completely abolish the seizures, but they can substantially reduce the number of seizures that patients may have. The new thing on the market which came is hypoglossal nerve stimulation for sleep apnea. It contracts the tongue muscle, and the sleep apnea is dramatically reduced in patients who are using the system. Spinal cord stimulation is primarily used for pain management, but some of our scientists in spinal cord injury research are now using it as a way to test if, by providing electrical stimulation to the spinal cord, one can improve locomotion or grasping function. And they're using either implanted systems or surface electrical stimulation systems. I will not talk about it today, I'm sorry, but as this field is just evolving and the first results are coming online. This is functional electrical stimulation system for cycling. I'm sure everybody who is working spinal cord injury has seen this type of things. They're used more as ergometer, as an exercise tool. These are FES systems for grasping and FES system for locomotion that I'll spend quite a bit of time today talking about. So functional electrical stimulation, what does it do? It's actually the same as electrical stimulation. The only difference is you target the particular muscles that are of interest. And if you're able to contract them in a coordinated manner and properly control the forces or torques that they're producing, you can actually generate very nice functions such as walking, standing, reaching, grasping, and such. And that's the basis of the field. With functional electrical stimulation, there are two main concepts, which are not really competing concepts, but there are two concepts. There's a neuroprosthetic approach, and there's a neuromodulation approach with the functional electrical stimulation. So we'll spend time on neuroprosthetic concept because it was the first one, and that's how electrical stimulation, functional electrical stimulation actually evolved as a field in the last 6 decades. The person who got an idea to actually design neuroprosthesis, this handsome gentleman, he is Vladimir Liberson, and his idea was that by stimulating actually tibialis anterior muscle and also peroneal nerve, you can deal with the drop foot stimulator. I'm sorry that this image is blurry, but that was the best one I could get from Oddstock drop foot stimulator. And the many other stimulators came in a pipeline, and I'll talk about them in a minute. But there are a couple of things which are relevant for neuroprosthesis assumption because they were quite prevalent for a long time. And when I joined the field in the 90s, they were kind of dominating the conversation. So first item is that patient spontaneous recovery does happen. It's limited. And it usually after 6 to 12 months after stroke or spinal cord injury, that spontaneous recovery is no more possible, and further improvements are not expected beyond the 6 to 12 months. And normally in that envelope or that type of thinking, the logic was then after 12 to 24 months, we should really consider using permanent neuroprosthetic solution to restore function, function being walking or transfer or grasping and whatnot. And we had two possible options. One was to have a surface electrical stimulation. Another one was to use implanted functional electrical stimulation system. And of course, the logic was that since you're implanting the systems, implanting electrodes, right on the nerve or right on the muscle, these should be much more selective. And by the fact that most of the hardware is in the body, the implanted system should be faster to put on and deliver the intervention. So I'll start with lower limb neuroprosthesis. So as I told you, the first that has been designed was neuroprosthesis for drop foot stimulation. There's many products out there, and I didn't choose this one to offend anybody. Bioness is something that's sitting on the market for quite some time. And the other one is Volcade, which is Canadian design, but they're both based on the work of Vladimir Liberson. And there are another two systems. One was designed in Europe. It's Actigate, which is fully implanted, except for one small part of the device, which is outside the body, which is a control unit. And there was a one which was designed actually in British Columbia. It's Neurostep, which was fully implanted, no external components to the system. What was interesting is that implanted versions, which were really having some exciting technical solutions and seemed quite promising, didn't caught momentum. And the reason for that may not have to be technical in nature, because from a technical point of view, both devices were quite good. But for one reason or another, the companies didn't manage to progress in a viable businesses, so to speak. So most of the field with respect to these drop foot stimulators are sticking to transcutaneous systems. They're simple, they're very successful. Thousands of patients are buying them, and thousands of these devices are sold and available. And they're quite helpful to stroke patients and other patients which have dorsiflexion problem. There's also much more complicated system compared to just drop foot stimulator is a system for locomotion. The original idea for that came from a Slovenian gentleman who is still alive. His name is Alois Kraj. And he actually used the peroneal nerve stimulation and added another 2 channels of electrical stimulation on major muscles in the thighs in order to enable standing up and locomotion. Daniel Graupe from Chicago took this idea, turned into a product just called Parastep, and that was the first FDA-approved FES system that we have and know of. What is interesting is that the system was fairly challenging to put on, required, and also when you want to walk with that, it really required a very strong upper body and also the commitment for the patient to use the device. So most of the people who use the device use it as an exercise tool to maintain their body, and not as much as something that you would use activities of daily living to walk to the washroom, to in your office and other things. And as a result, eventually, you know, those enthusiasts who like the system, they bought it. And then once we run out of the enthusiasts, then the limited number of systems had been sold. So even though it went through FDA approval and became a product, it didn't catch the storm. We didn't have thousands of people purchasing this system. There was an implanted version, which was done in Cleveland. Ron Triolo has been the lead on that project. This is the continuation, or in partnership with the efforts which were done for freehand system, which I'll talk, it's an upper limb system, which I'll talk about in a minute. I think Ron and his team have multiple patients implanted the system. They demonstrated its utility for walking, standing up, and maintaining standing posture. But as well, the system didn't become a product which is commercially available. The lessons learned from this is that whether the system was implanted or it's a surface stimulation system, it required quite a lot of time to set it up, and it required a lot of strength and commitment for the patients to use the system. Those people who have used the devices, especially implanted devices, they mostly use it for transfers, and the others, everybody used the systems for exercise. And as I said, limited number of systems have been implanted. Upper limb is slightly different. In upper limb, when I joined the field, which was in late 90s, this particular piece of technology emerged. It was called Bion. It was done by Jared Loeb. He was at that time professor at Kingston, at Queen's University here in Canada. And he designed this absolutely amazing thing, stunning thing, which was the whole electrode communications and control unit into something that is 2 millimeters thin, about 1.6 millimeters long, and which you can put in the muscle using a needle. And the idea was to use this to generate different grasping and reaching tasks, or prevent pressure ulcers, or even walk with the system. Although this was a really exciting and technological marvel of its time, it did not catch up. And I think there are a couple of issues with that, in my opinion, whatever that is worth, is that I think somebody did a study in Europe, I can't remember who exactly. They looked into the distance between the electrodes on a Bion, and found out that the amount of space or amount of tissue that they can actually activate to generate action potential was fairly limited. And that kind of coincided with the fact that in order to get a more complex or stronger movements, a person would need multiple Bions on a single muscle to get desired contractions. And the more Bions you have, because the system had limited bandwidth, communication bandwidth, then there was a limit in the controls that one was able to exercise on these units. And eventually, after a lot of trying and investment and exceptional engineering and clinical work, that didn't become a clinically viable product. The other product, which was totally outstanding and was clinically viable, was a freehand system, again, done at Cleveland. It's done by Hunter Peckham, who is another outstanding individual among the FES and neuroprosthesis researchers. The concept was not that simple. The concept was that you have a pacemaker-like device sitting in a chest. You have cabling which goes to different electrodes. These were called epimysical electrodes, which are attached on the muscle. And by stimulating different muscle groups, you can generate nice reaching and grasping, mostly grasping, but a little bit of reaching capabilities as well. They implanted quite a few patients with this system, and the company at some point in time stopped being financially viable. The exact reasons and how this all happened, I do not know, but I think probably 200 plus patients have received this implant. Amazing technology. What was interesting that when they were approaching patients who were eligible for these implants, about 1 in 30 patients opted for the system. And that's an interesting thing to find why. I think one of the challenges that the system had, it had a common ground, which was in the chest where the stimulator was. And then you had the electrodes wherever you wanted to stimulate the negative electrodes. Is this all okay? Okay, so you have electrodes where you wanted to stimulate the muscle. What was interesting is once you start increasing the stimulation intensity, there was a spillover current, and then some other muscles would be activated, which was not always desirable. So they use balance between intensity of stimulation and fixing some of the joints as a way to deal with the problem. Also, one of the challenges was they didn't really dedicate sufficient amount of occupational therapy or physiotherapy to help patients learn how to use the system better. And the putting the system on, the patient could do it themselves because it was designed for spinal cord injury patients. So you need somebody at home to put it on for you, and that will take 10-15 minutes to be done. So these are some of the challenges that these technologies have experienced. And the Bioness H200, that was designed by Roger Nathan in the 90s. When he came up with the technology, we all were absolutely amazed with that. And he essentially wanted to help patients, particularly stroke patients who cannot open and close the hand, to do it using electrical stimulation. And these units had been originally designed in Israel, and now they're all over the world, sold, and fairly successful product. What is interesting is this, besides being an amazing technology and really interesting solution, this is one of the very few systems that survived from 1990s and still is out there and it's being commercially viable. What is beautiful about it, takes you about 60 seconds to put it on. You just have to slide a hand into it and clap it and everything is in place. One drawback of this technology was, and we'll talk about it more a little bit later, is that when you stimulate the finger flexors, you don't get that naturally, you get this. So they had the orthotic system put in place so that wrist is fixed in this position. So when you stimulate these muscles really strongly, you get the fingers to do that. But if you didn't have an orthotic device to hold hand in this position, that would not look that much natural. And it was difficult, the controller and the whole setup was very difficult to use as a neuroprosthetic solution in activities of daily living. So that's why they migrated it to neuromodulation use, and I'll talk about it shortly about that. So these were the original assumptions that we discussed at the beginning, and this is actually what I think happened. Yes, we know that the patient's recovery, spontaneous recovery, is very limited. Yes, spontaneous recovery finishes after 6 to 12 months, but the expectation that patients will not further improve after that point has been debunked, because we had patients 30 plus years after stroke who, with neuromodulation tools, you were able to recover the hand function. So that's an important thing. Second thing is, because you can train them 15, 20 years after stroke or spinal cord injury, then one should not really consider using permanent neuroprosthetic solution before you explore neuromodulation option, which I will talk about it in a minute. The surface and implanted systems are equally viable. What was interesting that we thought that implantable electrodes will be more selective and you'll be able to get nicer and cleaner grasps. Sadly, the jury is still out there, because some of the FES systems that are producing, reaching, and grasping with surface stimulation electrodes gets actually as good or sometimes even better grasping outcomes than some of the implants. So it kind of puts an implant under a little bit of pressure to figure out how to do better, because they have a capacity and they should have a capacity to do it much better than they're doing it right now. And the fact that implanted systems can be put on faster was totally depending by Bioness L200, not H200, because you can put it on about 60 seconds. No implant that we know of can be turned on that fast or getting ready to function that fast. So the reality is neuroprostheses are outstanding technology. There's a huge potential, demonstrated utility with cochlear implants, deep brain stimulation, and drop foot stimulation. Walking and grasping are still ambitious goals, and I'm glad many people are working in the field and trying to move it forward. But technology still has a lot of room for improvement, especially with respect to interfaces, sensors, and control strategy. Neuromodulation concept. In my opinion, this is a FES 2.0 version. As we were designing neuroprosthetic systems for locomotion and grasping, something interesting happened. People start improving their function, voluntary function. So the idea of using FES technologies or TOSes or prosthetic system was challenged by the idea that maybe you should use it as a therapeutic tool. Dan Popovic, Thierry Keller, and myself wrote an article about that in 2002, when most of the people didn't really fully believe that and thought that this is viable. But the time proved Dan and us and Thierry actually correct, substantially correct. So the first person actually to spot the neuromodulation changes or this neuroplasticity was this handsome gentleman. This is Roberto Marletti. He lives in Italy. He is now the internationally recognized guru for EEG signal processing and analysis. But in 75 and 78, he actually ran studies with FES systems, neuroprosthesis for grasping, which was designed in Ljubljana, and neuroprosthesis for locomotion, drop foot stimulator specifically, that were also designed in Ljubljana at that time. And he, both of those studies observed, at that time were called not neuromodulation, but carryover effect, that patients who've been trained with these systems improved voluntary function. And then he published these wonderful papers, and nobody actually paid attention to this until this gentleman redid the study with Artur Prokaska's system for grasping in late 90s. And he also found this carryover effect. This is Dan Popovic, who sadly died last year. And he and others start looking into using neuroprosthesis as a therapeutic tool. And the concepts that came out of Dan's initial study and others in early neuromodulation phase of research was that patients have capacity to recover only if they have some residual function. So it doesn't have to be very good, but as long as they can do a little bit with their hand or foot, they're much better candidates for neuromodulation or functional electrical stimulation therapy. The task should be functionally meaningful, and you have to do it repetitively, which is fine. And then the earlier the person starts, the better outcomes will be done, will be achieved. And also that FES movements that you try to induce with this neuromodulation, you can have them as a single muscle or two muscle or single or two joint type of stimulation. And the overall desire, and desire still exists today in industry, is that they wanted to have this technology delivered, hopefully without the therapist. So how does the functional electrical stimulation therapy work, or neuromodulation, how it works? So because many of the people today are spinal cord injury people, so I'm just going to give you that example. So imagine you have a person who had a spinal cord injury, let's say at the cervical level, like C5. And what you would do is you will ask the patient to imagine a particular reaching or grasping task. And as the patient is imagining that, and the brain is trying to send a command to the spinal cord, and that command cannot proceed to the muscle or groups of muscles responsible for performing that task, what you do is you fire electrical stimulation and get the particular movement carried out with electrical stimulation. As a result of that, the sensory feedback comes to the spinal cord, and then bounces back to the upper layers of the central nervous system. As you do this repetitively, you essentially create completely new pathways in upper layer of the central nervous system, if this is required, and as well in the spinal cord itself. And then the new connection is created with the peripheral muscle, and the patient is able to perform the task voluntarily. So the lower limb. So the first person to observe after Marletti, to observe the neuromodulation and report on it, was Dick Stein, who also passed away a few years back. And he used his KITE system to do it. What was interesting was that he had a very noticeable neuromodulation effect. It didn't work with all patients, and some patients generally found drop foot stimulation quite painful. But what was interesting, even though you had the carryover effect, and even though you had neuromodulation effect, the patients were still better off using the neuroprosthesis daily than just depending on neuromodulation effects that the technology was providing to them. The other technology that actually our team in Toronto has put together was actually a 8-channel FES system for locomotion, and it's targeting all major movers during the gait. We have used it in spinal cord injury patients, and we have used it in stroke patients. Stroke patients not that successfully because we underestimated the dose needed for the patients. But anyway, the principles of this is very different from the drop foot stimulator. The drop foot stimulator activates this reflex that one has when they step on something sharp to move the foot away. This particular mode of electrical stimulation is designed to actually generate the natural locomotion cycle. And we've done it with quite a few patients. And what was interesting is that it works quite well for a large number of patients, but not for all patients. The patients who, especially in spinal cord injury space, and even in stroke, the patients who were able to regulate their balance to some extent, or a little bit better, they did much better than the patients who had no ability to regulate the balance. At the beginning, you need 2 therapists to start the program because usually patients are not in that good shape when you start the program. But as you teach them how to use electrical stimulation and walk on a treadmill, suspended, and their weight kind of balanced or partial weight taken off, they, with time, learn how to do it on their own, and they can actually go through this locomotion themselves. I'm not going to show you those videos, but trust me on that one. Many patients recover locomotion function as a result of that, but here's a catch. They can recover the function, they can walk, and they can walk with the walkers and whatever they do. But if they get something like a pneumonia, or you get some disease that hits them and puts them back into bed, which with spinal cord injury patients and stroke patients does happen, when they get out of that situation and they want to go back to walking, by that time they may be deconditioned. So what would be really helpful is for these type of patients to have regular maintenance, and especially if they have an event like I was just explaining about. In upper limb, the BioNS people essentially transition from using it as a prosthetic device to neuromodulation use. Beauty of it, it's easy to use. There's tons of clinics who use the system, and targeted population is usually people who have higher functional strokes, who can do the reaching, put the arm in a space, but they need to learn how to open and close the hand. The challenge, again, as I spoke earlier with this technology, is that the way how you stimulate the finger flexor muscles is not necessarily representing the way how the central nervous system would do this naturally, and would not create a natural looking grasp if it was not for orthosis. As a result of that, the attempts to run a randomized controlled trials to prove that this technology is able to profoundly act as a neuromodulation tool have not been very successful. The technology that, so warning, this is my move technology. The other competing technology was similar to locomotion system is functional electrical stimulation of the reaching and grasping. Here you have about 8 channels of electrical stimulation. You can put on different muscles and muscle groups to get reaching and grasping. And whatchamacallit, there's about 30 something, 35, 40 different protocols. Some of them are for spinal cord, some of them for stroke specific. That enables a patient who may not have any function in their arm and hand be able to reach and grasp and pick objects. We also stimulate intrinsic muscles to get fine motor control. And what you can get reaching and grasping tasks. You can do, tripod grasp, lumbrical grasp, key grasp, and even bimanual types of tasks. I'll just show you one of the videos of how MyndMove system works. This is one of the most complex things you can do with a stroke patient. This is a stroke patient 4 or 5 years after stroke, and it's the first time he's receiving MyndMove therapy. And the task for him is to, flex the biceps, extend the arm, extend the elbow, and try to extend the fingers. Every component of the movement is done with electrical stimulation. Catherine, who is helping with the process, is actually just making sure that the hand is moving physiologically correct. Why is that important? Electrical stimulation, unlike robotic systems, does not have capabilities to control the angle of the joint very precisely. So because of that, especially in a complex movement like this one, the therapist may need to guide the hand and arm in the direction where they want to move that. The patient doesn't have to be without a t-shirt to do the therapy and things like that. And usually this is delivered by a single therapist. In this particular case, this gentleman had a problem with sitting and keeping his legs on the floor properly to be able to do this reaching and grasping task. That's why we had a physiotherapist just making sure that he's sitting properly, but everything in this protocol is actually delivered by electrical stimulation. At the beginning, these protocols are very slow. It takes time for patients to deal with their tone, to deal with, atrophied muscles and all other things. And so maybe in the first session, if they want to do reaching and like finger extension in this type of posture, you can do it 4 or 5 of these movements in a minute. And then with time that gets faster and the hand starts going smoother. And so you can do about 5 or 6 different reaching or grasping exercises during the session. Normally patients receive about 40 hours of therapy. We first focus on shoulder and elbow, and then you move further distally to work on wrist and fingers and whatnot. The key element here is patient really has to be engaged, has to think what they're doing, and has to really attempt to perform the task that you're asking them to do. You need a competent therapist to navigate the treatment. This cannot be done without a therapist, and you need an FES device that can provide this sophisticated reaching, grasping movements that you need to teach the patient. Here's a stroke patient before and after. So this is, he was about 9 months after stroke when this was recorded, and we worked with him using MyndMove technology. And you will see what he was able to do after the treatment was over. So this is before the treatment. This is Toronto hand function test, and it's a phone task, picking up the phone and putting it to the ear. And you can see he cannot even grasp it. And then you'll see what happens at the end of the treatment. This is not age related, so don't, I showed Andrew's pictures, but it has nothing to do with the age. We had people who were 87 and they went through that successfully. This is a spinal cord injury, same technology, same thing. The only thing is here we work bimanually. In stroke, we only work on one arm. And you can see part of the Toronto hand function test that he's trying to grab the bar and try to hold it, and then we push it to the side to see if he's able to control eccentric loads in the hand. So it's like holding a frying pan type of situation, or a baseball bat. Not that he's going to go and play baseball, but it's equivalent to that. And you can see that. Okay. This is an old video from late 2000, 2009, 2010. But what I like about it is that when he is actually opening his pouch, pulls his palm at that time and does whatever he needs to do to turn it off and put it back. So just shows you how that actually hand looks in real life after the treatment. The lessons learned: the change in function using neuromodulation option for upper limb is quite transformative. The good outcomes can be achieved both in stroke and spinal cord injury patients. It works well with other patient populations. We even had it in patients who had brachiopraxis injury, cerebral palsy, and whatnot. The challenge with this technology is therapists actually need time to master the complex protocols. The protocols up to 4 channels, they come natural, and it's fairly easy for therapists to figure out how to use them. But when you have this 8-channel protocols or bimanual protocols, that could be intimidating at times. Donning and doffing requires time, and this is something that we need to deal with that. And currently replacing electrodes and cabling definitely needs an improvement, right? But this is a state of the art, and right now with this type of technology, you can get quite a bit done with the patients. So you remember the original assumptions? So first assumption, the patients have to have some residual function in order to restore function. That has been gone out. You can take a patient who has no movement in the arm or a hand, or both, and you can apply functional electrical stimulation therapy and restore their reaching and grasping. Tasks should be functionally meaningful, and they have to be repetitive. That's clear. The earlier you start with the person, the better. But you can start even with people who are 25 years, 30 years after stroke. We've done it. We had some good results with that. The FES-induced movement should not be single joint movements. They have to replicate reaching or grasping patterns that we normally use in activities daily living. That really helps learn those tasks much, much faster. And you get much greater scores and much greater outcomes. And the idea that FES can be delivered, therapy can be delivered without a therapist, I am not buying that at all. And all the results that we have seen so far suggest that this is not the way to go. You need the therapist engaged to guide the patient, to guide the protocol, and with that, you get the best outcome. In a summary, the neuromodulation technology is clinically effective in hand and arm function, and it's effective in walking function, but you need to be prepared to maintain the patient after they finish the therapy. Technology has a lot of room for further improvement. Putting the electrodes on and taking them off should be easier and faster. The discomfort could be dealt with. As you've seen it, we changed the pulses and we made an improvement in that space. So I would encourage those of you who like that type of research to look in other and different types of pulses. What else can we do to reduce the pain and discomfort? Because that sometimes can be a limiting factor. We need new targets and new stimulation modalities. And like standing and sitting balance function have to be added to locomotion therapy, because locomotion alone is not sufficient. You should do balance and standing up and sitting. You need to master this task before one should go into the walking. And we also need to simplify the way how the therapies are delivered and interfaces are done, because there's a lot of room in that space to improve this. So future FES is a tricky business, right? I mean, when you look at Nikola Tesla, who invented the 20th century, when you look at his articles, and I'm not going to bore you with that today, well, half of the time he totally missed the mark. Some things he was very good in predicting, and some things he was totally off. So whatever I say today, probably you can discard about 70% of that. because making any predictions, it's extremely difficult. But these are a few things that I think are relevant, and we should look into them, and I'll go one by one, discuss them. So better interfaces. Right now, we are not able to actually selectively, nicely stimulate one nerve bundle. And in the nerve fiber, peripheral nerve, you have multiple bundles. And forget about individual, like on the left side of the screen, like individual nerve fibers. We have no capacity to do that. There is a need to improve technology and move into that space. Ability to do that and do it effectively will dramatically improve the FES field. And this is where is one of the main battlegrounds in the space. These are the surface stimulation electrodes which we use today. And depending how you place it and how much current you deliver to it, you may have different, you may result in a different postures of the arm. So knowing where to put the electrodes with the existing electrodes today and have it always repeatable outcomes has been a challenge for many of the scientists and researchers. Some of the recipes that work very well have been incorporated in my move therapy, but you should be able to figure them out yourself if you want to do that. But that's a constant challenge. So we need way better interface than that. We believe that the garments are the right solution. You should be able to integrate electrodes into the garments. And this is one of our prototypes from 6-7 years ago to generate reaching and grasping and whatnot. We are still working on this technology. It is not ready for prime time, but I personally believe that this is something that has a good potential for neuromodulation therapy, even for neuroprosthetic applications, and we should look into that. And we need smarter people that need to look into that space and try to help us solve this issue. With respect to implantable technologies, there are different types of systems that are coming. On the left side, you have a Cleveland Group solution, and I think on the right side, I think this is from Freiburg, and there are other places. Everybody's trying to come up with electrodes that will be better for stimulating peripheral nerves. I don't think we're there yet. We're trying really hard, but that's going to be a place where this whole field can grow and do much better than it's doing right now. Better stimulation pulses. The only comment I want to say is when we came up with these pulses a couple of years back and patented them, at that time, we didn't think it was possible to create pulses which are less painful and more appealing to the patients. The fact that we found a solution suggests that this field is still wide open and that people who are in this space should continue doing research to find out which type of pulses and profiles could produce very good muscle contractions and good stimulation while minimizing the pain and discomfort. I think that's something that people should continue working and looking into it in the coming years. These are the cables and connectors that we use in surface electrical stimulation. And by the way, they look like they were designed in the 80s, and they're still like that today. So this is terrible. I just wrote a grant to improve on that one, and I was rejected because what I was doing was mundane or stupid, or there's no research in it. The technology that we have today for electrical stimulation and cabling and connectors is absolutely terrible and needs total rethinking. With implants, the situation is gently better, but profoundly the same. So the connectors and cabling for neuroimplants is still something where I expect the field to grow and evolve and do much better than we are doing today. Control systems. When somebody tells you we're doing closed loop control of functional electrical stimulation, they're probably fuzzing you. This is actually one of the only functional electrical stimulation systems, closed loop system, that is very easy to put on, and we've tested in 10+ subjects, and you can see how it works. And that's a single joint. We need systems that can do it for multiple joints very reliably in order to improve locomotion and balance and standing in patients. And this is something that we need to put some focus and energy into. Some people have been working on that, like Kristen Musselman and Kay Masani, but this is what needs to be done for multiple joints as well. Interfaces and putting the electrodes and the cabling and all these things can be quite complicated and intimidating. That has to be simplified, and the training and how it's delivered and how it's done has to be dramatically simplified in order to enable more people to use the technology and to make technology more appealing, both to the practitioners, physiotherapists, occupational therapists, but also for the patients. BCIs, I think the brain-machine interface systems, as Ashraf and I spoke earlier today, need to be integrated with functional electrical stimulations. We have some really good clinical outcomes lately with this. I think ability of the patient to trigger FES system volitionally using the brain-machine interface is an excellent neurotherapeutic tool and neuromodulation tool. So I encourage you all to look into that if this is something of interest. And the final point, I have nothing intelligent to tell you about artificial intelligence, but what is really scary is that whole universe is going up and using artificial intelligence for all kinds of things. And in functional electrical stimulation field, there's very little to almost nothing. So we need to get on the wagon and start looking into this more carefully and more thoughtfully. Conclusions: functional electrical stimulation is an amazing technology. It's actually a universal interface between a device and neuromuscular system. And the neuroprostheses, such as systems for hearing loss, for movement disorders, for sleep apnea and drop foot, are quite effective, and they've been out there and making some major successes and improvements in lives of many people. On the neuromodulation side, hand and arm function are working quite well from the point of view of restoring the function using neuromodulation tools or functional electrical stimulation therapy. Walking function is, we're still working on it, and some products can be expected in the near future in that space. We are still in very early stage of this field, of functional electrical stimulation field, and there's new and exciting neuromodulation systems that are yet to come. Some of them are for bladder management. This is from Paul Yu from University of Toronto, which is a surface electrical stimulation and has really exciting outcomes. Then treatment of mood disorders with electrical stimulation, and stem cells production and navigation as an implanted technology. So watch for these. I think they're going to come soon, and you see them in various journal papers and whatnot. And some of them have really great promise. Acknowledgements: these are all the granting agencies who were kind to me for the last 20 plus years. And special thanks goes to Dean Connor and Mario Suffelman, and Marian Walter Schroeder, who had repetitively donated to us and helped us move the field forward. And if you want to find the papers that we published and whatnot, this is the easiest way to access that, and other information on our webpage and Twitter. And this is the organization that pays my bills, salary. Thank you. I'm open to questions. And
so, Dr. Popovic, thank you so much for this amazing lecture. And we are like 10 minutes over the time, but we will allow 2 questions. This is amazing lecture. One of the best FES lecture that I had in many years. Thank you so much for this. So we will open the panel for 2 questions to Dr. Popovic. If anybody has interest in asking 1 or 2 questions. I have one quick question for you. You mentioned early on before the presentation the application of FES in conditions like sleep apnea, depressions. Can you speak a little bit about this? I know that the time is limited, but just briefly, where is the field stands up on this new application?
So sleep apnea is actually a product. I can't remember for life of me the name of the company right now. Paul Meadows is one of the people who was involved with this technology. It's a simple single channel electrical stimulation It's implanted, and it works quite well. And I know that it's in the market, and there's more and more patients who are receiving it. And that came from the company in California. And the company got bought or something. There's some merging or merger acquisition event that I'm not 100% sure about it, but I know the technology is there and it's quite effective. The depression study, there's some initial data published about 2-3 years ago by stimulating facial expression of Duchenne marker. You can generate a genuine smile, which is not the smile that you can control voluntarily. There's a smile that is generated by limbic system without involving the frontal lobe and cortex. And that smile and facial expression gives an expression to people who are looking at you that you're genuinely happy. And this is the expression you make when you're laughing and giggling about something silly and whatnot. And we artificially create that facial expression for 10 seconds on, 10 seconds off. And by doing that, we were able to change on a Hamilton depression scale patients from wherever they were usually moderate or severe depressed patients, to dramatically drop their severity in depression. And out of 10 patients that we treated, I think 5 actually got cured because the numbers are below 7 points. This is an initial study that was done in a selected group of patients, and now we're looking to do randomized control trial, and our psychiatrist, Dr. Venkat Bhagat, is looking into running a larger scale clinical trial using that, and we're preparing technology for that. So it's very interesting, very exciting, because there are no side effects, there's nothing. And if that works, that'll be a very elegant way to treat depression at home. Okay. Valerie, you hear the question?
Hi, yeah, thank you so much for the great webinar. I've learned a lot. I just wondering, I'm curious about the electorate position. So just wondering if you put them on the predefined locations to apply the simulation or for a specific task, or you do have do some sort of assessment based on the patient's condition first and then put the electrodes. So the reason I'm asking, because I think that it's as an example, for stroke, people might affect differently. So yeah, just.
Right. So there are two lines of thought. Unfortunately, I had only 60 minutes, so I had to choose some winners and ignore some really exciting work that was done by others, like Thierry Keller and Dan Popovic spent about 10-15 years building electrodes which are like mesh, and they created systems when you automatically select where the electrode should be from that mesh of like a matrix of electrodes, right? And we went the opposite direction. We wanted to get the same function by getting really large electrodes, because it's easier for therapists to put and they don't have to think too much. For MyndMove technology, we were able actually to find really nice recipes where the electrodes has to be, and almost in every patient, it gets you what you need to get. You may need to move the electrode a little bit from patient to patient, but general locations are quite accurate. And except for finger flexion, where you need 2 electrodes, which are a little bit more finicky to place, everything else is really straightforward. So if you want to get scapula muscles, all the positions of scapular muscles which are in there are very reliable. So on each patient you put, whether they're stroke or spinal cord, you should be getting the outcomes. Spinal cord are a little bit problematic because some of them, they have peripheral nerve damage, and then you may not be able to get all the muscles that you would like to get. In stroke, that's piece of cake, it's not an issue. But in spinal cord, you may need to move an electrode a little bit and a little bit explore to see if you can get another component of the muscle, compartment of the muscle that is further along the muscle or more distal or more proximal, right? But the recipes that we have been working for on the last 15, 20 years are very stable. So if you follow some of those papers or you get the MyndMove instruction manual, the location of these electrodes is fairly robust. So even the person who is naive or new to this, by putting electrodes in this location should get that function fairly reasonable. Now, here's the catch. When you do it for the first time, the patient may respond really funny. And even if you look at the forces which they're producing, they can be erratic and all over the place. Don't get disenchanted by the first session. Do it like if everything is normal, behave like everything is okay. And then the second session, after the third session, the hand will start coming exactly to the right posture, doing the right thing. Why is this like that? I do not know, and I cannot explain it to you, but we know for a fact that the first session is kind of introduction session, and the more you stimulate them, they slowly start coming into having right posture of their arm, like flexing on the fingers, and all the responses that you look for. So don't get disenchanted if on a day one you put the electrodes on a person and you stimulate them, and they, instead of getting that, you get this. It's okay. Just keep going, like as everything is as it should be. After the second and third session, these fingers are going to come in like that, no problem. Okay.
Well, Dr. Popovic, thank you so much again for this amazing lecture, and thanks to the audience for attending. And again, our apology for delay starting because of technical issues. And thanks to the ACRM and to the community webinar and to the FES and Technology Task Force. And looking forward to organize future meetings and future webinar. And please email us your feedback about Dr. Popovic session and webinar, and what else you are interested to listen to in the future. Also, I remind you with the annual meeting early in November, November 8th to November 11th, and hopefully you can attend the annual meeting. Thank you so much.
Thank you. Thank you, Ashraf. Thanks, Christine, for inviting me. I really appreciate it.